Okay. Yeah, thank you for the introduction. My name is Christopher. I'm going to present to you page table randomization. This is joint work with my collaborators from TU Darmstadt and Luca Davi, who now changed to the University of Duisburg-Essen. So to give you a little bit background on the impact of kernel attacks, so here we have the classic architecture of modern operating systems, where you have some privileged code, which is better known as the operating system kernel, which manages memory, sets CPU registers, flags, and provides an interface for external hardware in the form of drivers, and also, which is very important, manages the and enforces the security for the overall system. This one is directly operating on the hardware, and on top of the operating system, we have user mode processes where applications like browsers or document viewers can be executed. And these processes are isolated from the kernel and from each other. And as you can already see here, these browsers or document viewers are applications with a fairly large code base, which makes them actually prone to software vulnerabilities. So this is why in the usual case nowadays, they run at lower privilege than other user processes to make sure that even if an attacker can exploit a vulnerability within one of these applications, he cannot access the rest of the system. Unfortunately, though, the operating system kernel is also fairly large and fairly complex, and therefore also prone to software vulnerabilities. And an attacker can actually use the previously compromised process with lower privileges as a pivot point to then attack the operating system, for example, with a code reuse attack, like return-oriented programming, to then compromise all of the system. Fortunately, there has been some work in the past to mitigate these code reuse attacks. In particular, CFI seems to be one promising approach to mitigate these kind of attacks. And actually, we just see in the beginning of this month that GR Security released their own CFI implementation for the Linux kernel, which actually promises to end all code reuse attacks for the Linux kernel. So the question is now, is this enough? Are we done? Are we finished? Did we solve the problem of memory corruption attacks? So, and for that we can, if we look at CFI, on the one side it actually provides a fairly good protection against control flow hijacking attacks. That is when the attacker uses a memory corruption vulnerability to actually override a code pointer. On the other hand, we know that CFI cannot mitigate non-control data attacks, which are also known as data-only attacks. The thing is, with data-only attacks, their effectiveness highly depends on the target application. So, for example, in the past, they have been shown to be used to extract cryptographic key. But one important limitation of these data-only attacks is that they cannot introduce new functionality. At least that's what was commonly assumed. So let's have a look how these data-only attacks work in the context of kernels. And in order to do that, I have to refresh in your memory a little bit how virtual memory works, and in particular, what's the role of page tables in there. So on the right-hand side, you can see the physical memory, and on the left-hand side, we have the virtual memory, which is some form of abstraction where software actually operates on. And as you can see, the virtual memory has different attributes. So when software now tries to access some virtual memory, the CPU will actually use the memory management unit, which is a dedicated hardware unit, to translate this virtual address to a physical address. And what the MMU does, it will first look up a pointer to the so-called page table hierarchy, and then use the virtual address to traverse this page table hierarchy to a page table entry, which then contains the translation information, so the physical address, but also some permission bits. And as you can see in this case, the permission for accessing read-write is set to 1, so true. So the access is granted and the address is translated to the physical address. So to summarize, the page tables are super important, not only for the translation, but also for the permission enforcement, so how virtual memory can be accessed. And yeah, it would be too bad if somebody tampers with that. So what I'm going to show you next is an attack where an attacker uses the data-only attack against page tables on a CFI hardened kernel to actually gain arbitrary code execution. So again, the attacker starts as a user, then exploit a kernel vulnerability, and after some fancy magic, we actually end up with root. So what exactly happened here? What the attacker does, it uses the memory corruption vulnerability to locate and then overwrite an entry of a kernel page table entry. In particular, he will change the permissions bit of another code page, which might contain a system call, to mark it as read-write-execute, so that he can use the very same memory corruption vulnerability again to actually override the system call with an own shellcode. And then when he triggers the shellcode, he will execute arbitrary code. So the problem itself is not completely unknown. So there has been some previous work which try to ensure the integrity of the page tables. But the problem with with the related work is actually that they either require some form of hardware trust anchor, that they depend on a higher or more privileged execution layer like a hypervisor, or that they have inefficient checks actually for enforcing the integrity. For example, you can imagine that the kernel keeps the page tables as read-only for the whole time, then maps them as read-writable when there's a change to be applied, and then maps them to read-only again. This is not only inefficient, but also opens actually a small attack window for the attacker, where you can also apply some malicious changes. So our approach is now to apply randomization to the page tables to get rid of the hardware requirements and have low performance overhead. Before I give you the details of that, let me quickly introduce talk about the assumptions in the threat model. So we assume that return to user and similar attacks are prevented by modern CVU features. We assume that the attacker can actually not inject arbitrary code into the kernel, which is also known as data execution prevention, or writable or executable. And we assume that defense like CFI is in place to mitigate code use attacks. On the other hand, we assume that the attacker has successfully compromised user application and can exercise a kernel vulnerability to read or write from or to known addresses. So an abstracted view of the kernel is that we have this code section, and then we have a data section. And within the data section, we actually have the page tables and also kernel structures which contain pointers to the page table. And if you look at the address space of a 64-bit system, you actually will discover it's huge. And it's so huge that there's actually some unused memory, which is up to like 1 terabyte, which is not used at all. So what we can do is we move the page tables to a random location within this unused memory region, and then protect all the pointers such that the virtual address of the original location where it pointed to can only be resolved with the randomization secret. And while the high-level idea may seem relatively straightforward, we've actually faced some challenges during the implementation of our work. And one is that the kernel actually does contain many references to the page tables. And this is partially due to that ptrand is only activated not right in the beginning of the boot, but in the middle of the boot. The reason for that being that the kernel, when it starts and actually switches to virtual memory, it depends on a certain memory layout, and it has a fixed set of page tables which it depends on. So once we switch to the kernel switch to virtual memory, we then activate ptrand and relocate the existing page table entries to the randomized area and convert all the existing pointers to physical addresses. Further, we then had to modify all the code that actually manages the page tables, so especially being the code that traverses the page table hierarchy, and also the code that allocates new memory for page table entries to work with the physical addresses and involve the randomization secret as needed. We also had to make sure that the randomization secret is protected from being leaked to the attacker, and we do that by storing it in a debug register and making sure that this one is actually never leaked to the readable memory. And finally, there were some Linux specifics. Linux has a one-to-one mapping of the whole physical memory into the virtual memory. And of course, the attacker could exploit this to access the page table since he knows the physical address. So what we did, we actually removed the page tables from the FusMap. We could not just deactivate it because the Linux kernel actually depends on and using this one for also some other stuff. Now coming to the evaluation, similar to other randomization schemes, we have to consider two main attack vectors, which are guessing attacks, so that the attacker just guesses the right location because of low entropy, and memory disclosure attacks, where there's some form of reference in the memory to the page tables. For guessing attacks, we found that for an average desktop system which executes some applications, the probability is actually fairly low that the attacker can guess the correct page table entry, the address of the page table entry. And we then also looked at our main server, which at that point in time had 9 parallel VMs running. It's and like 64 gigs of RAM. And we see the chances here actually don't significantly increase, but are still very low. And in fact, it's more likely that if the attacker try to fill the memory with page table entries, that we run into a denial of service attack before the attacker can, because the system runs out of memory, before the attacker can actually increase the chances up to a point where he can guess the correct address. For memory disclosure attacks, we protect all the pointers to the page tables by converting them to physical addresses. And to make sure that the register is not spilled, the debug register, we actually ensured that this is never spilled during interrupts. And we actually disable software interrupts during page table walks to prevent that possible intermediate values which are used during some calculation can be leaked through general purpose registers. We implemented ptrand for Linux kernel with the version 4.6 and enabled return address protection, so the CFI for the Linux kernel, and evaluated it on an i7 with a Debian as a base distribution. And as you can see here, we had, and for our performance evaluation, we used spec to evaluate CPU intensive benchmarks. And as it comes of no surprise, we don't see any overhead here. We used Phoronix to execute some macro benchmarks, and there's, again, no overhead, no really visible overhead. Where we do actually see some overhead is for micro benchmarks, in particular for when we create new processes. And this is kind of expected because when you create processes, you do the most things with the page tables. We need to allocate them and set them up. And in Chromium, we actually see some form of overhead. I think in percentage, it was around 9%, so it's non-negligible. But if we look at the total time, it's still below 1 millisecond. And we think that it's actually OK to trade off below 1 millisecond to have some good protection. The runtime overhead, the runtime performance is not affected at all. In fact, we see some performance improvements, which is probably more likely to be some measurement inaccuracy. So to conclude my talk, I hope I convinced you that page table attacks are a serious threat to kernel security. We presented the first randomization-based defense for page table against data-only attacks. We have no dependencies on some extra special hardware or privileged execution modes, and our solution complements well code reuse defenses like CFI. Our proof of concept implementation showed negligible overhead, and we do not affect the overall stability of the operating system. Thank you very much, and I'm now happy to take any questions.